Thanks for the introduction. So, hello everyone. What I want to present is a joint work with my supervisor, Simon Apers, and I'm a student at IRIF in Paris. So, let me start by defining all of the appearing complexity classes of my talk. In contrast to UPenn, I will not use circuits for my definitions, but Turing machines. So let's start with deterministic log space. One way to define it is, as all the decision problems that can be solved by a Turing machine that has access to two tapes, a read-only input tape and a read and write work tape, where the space restriction only counts for the work tape. And then there's also non-deterministic log space, where in addition, we also have a third tape, which is a read-only certificate tape. And then naturally, we can also define BPL, where we replace the certificate tape with a read-only random coins tape. And yeah, as usually we want to, for BPL, we want to distinguish yes and no instances with bounded error. And then we can also define bounded error quantum log space in this way, where we replace this random coins tape with a quantum work tape. And here we also have a space restriction on this quantum work tape. And the tape cells of this tape are all qubits, and they are initialized in state 0 at the start of the computation. And we have two tape heads moving on the tape. And at each step during the computation, we can do two things. Either we can apply a unitary from some fixed unitary universal gate set, say Hadamard T and C naught, or we can apply a measurement in the standard basis. And then the measurement outcome is told to the transition function of the machine, or we access a special state, depending on whether outcome was 0 or 1. So yeah, our BQL definition implicitly contains intermediate measurements, but as UPenn mentioned, it's even equivalent without intermediate measurements. Okay, so this is a little overview of how these classes relate. So some of these inclusions are trivial, for example, L being an NL, of course, because you can just ignore the certificate. L is, of course, also in BPL because we need not use the randomness. Also, BPL is in BQL because it's also quite easy. We allowed the intermediate measurement, so we can just apply a Hadamard measure and then get a random outcome. And the last two inclusions are not completely trivial. The one NL being an L squared. And by the way, L squared means all problems decidable by a deterministic machine and space log squared n. This inclusion is exactly Savage theorem from 1970. And then also BQL is contained in L squared, which was shown by Watrous in 1999. Okay, let me also mention some very important computational problems in the space-bounded setting. For one, there's directed ST connectivity, which will be the main actor in this talk. That is the problem where we are given a directed graph and two nodes S and T, and we want to decide if there is a path from S to T. And this problem is well known to be NL complete. The hardness is because you can see it as the configuration graph of an NL machine. So essentially, you want to decide if there's a computation path from the start configuration S to an accepting configuration T. And the containment follows easily also because the certificate can tell you the path. And there's also the undirected version of it, USTCon, where instead of a directed graph, we're given an undirected graph. I want to decide if S and T are connected. And there's a very easy randomized space-efficient algorithm, which is essentially just do a random walk starting at S for some polynomial number of steps and see if you find T after some time. And it is known that for undirected graphs, after polynomial number of steps, you are expected to find T if they are connected. And the algorithm is space efficient because essentially you just need to keep track of the current node you are at and have a timer to know when to terminate the algorithm. And then the problem was shown by Reingold to be already in deterministic log space, and it's known to be complete for that. Okay, and then one last problem, which is polyconditioned matrix inversion. This was shown by Taj-Ma in 2013 to be possible in quantum log space. So the problem is that we're given an n by n matrix A, which we know is well conditioned. That is the spectral norm of A times the spectral norm of A inverse needs to be polynomially bounded. Then we can estimate the inverse entries of A with inverse polynomial accuracy. And in fact, yeah, the problem is even BQA complete. And there are many more linear algebraic problems of this sort, which are also BQA complete. For example, computing or estimating the determinant or powering matrices or sampling eigenvalues of Hermitian matrices. So our picture looks kind of like this. And a very natural question is, of course, whether we can find a non-trivial relationship between NL and BQA. Can we maybe show a quantum advantage for ST connectivity? And our main result is that for a restricted class of ST-con instances, we can in fact find a quantum log space algorithm for which instances they seem hard classically. So yeah, before getting into the result in more detail, let me mention maybe why the result would even be unexpected. And for this, let me talk a bit about random walks again. So for undirected graphs, I already said that we can efficiently decide UST-con by doing a random walk. And essentially, the reason is that the hitting time for undirected graphs is polynomially bounded. That is, if S and T are connected after n cubed steps, we're expected to find T from S. And this directly corresponds also to spectral properties of the random walk Laplacian, for which we know that the spectral gap, so the smallest non-zero eigenvalue of the Laplacian, is inverse polynomially bounded. And then this would also very directly give a BQL algorithm. For example, I don't want to get into too much detail, but one could estimate the kernel dimension, which would allow to count the number of connected components, which would even be harder than deciding if S and T are connected. For directed graphs, random walks are not that well behaved. An example is given here. So in this graph, if we start a random walk from S, it's quite easy to see that we are expected to stay in this left component of the graph for a very long time until we cross this bottleneck to the right part. And also, we again have this correspondence that in this case, the Laplacian need not be diagonalizable, but the smallest non-zero singular value is only inverse exponentially bounded, not polynomially bounded. So at a first glance, it seems not obvious how linear algebraic quantum log space procedure could be of any help here. But nevertheless, this seems to, or this turns out to be the case. So let me now present our results. And for this, let's denote by n of ij the number of paths between two nodes I and j. And then, yeah, our main result is that if we are given a graph where the number of paths from I to j are polynomially bounded, then we can decide ST connectivity. We can even count the number of paths. Yeah, and one example is this graph here, where it's also easy to see again that if we would do a random walk starting from S, then we would not be expected to find T because we are likely to abort our path from S to T for some short path early on. So a random walk would have inverse exponential probability to hit T. Okay, so let me sketch the proof. First of all, we can assume without loss of generality that we are given a directed acyclic graph. Otherwise, there's a well-known reduction that any possibly non-DAG can be reduced to a layered graph, which is guaranteed to be a DAG. And then we look at the following matrix L, which is the identity minus the adjacency matrix. We called this the counting Laplacian. I was somewhat amused that I heard Ted Pine call it the typo Laplacian, because somehow it's very unusual that you put identity and adjacency matrix together, but you would expect maybe the degree matrix minus A or identity minus random walk matrix. But it turns out to be useful to define it like this, because we find that the inverse of this matrix L is equal to this truncated Neumann series. Because if the graph is a DAG, we know that the adjacency matrix is nilpotent. And then it is an easy observation that the power of the adjacency matrix, so the entries of A to the K of ij, exactly correspond or are equal to the number of paths from I to j of length exactly k. So if we sum up all of these different powers of the adjacency matrix, we are exactly summing up the paths for every different length. So the inverse is just equal to the total number of paths between I and j. Yeah, and then I mentioned before that polyconditional matrix inversion is in BQL. We want to use, ideally, that we can invert this matrix L. So the question is, when is this matrix L polyconditioned? For this, we can just check the spectral norm of L and L inverse. Let's start with the spectral norm of L, which is actually the uninteresting case. So we can use the equivalence norm of spectral norm and max norm, where this is the maximum entry and magnitude. And they are related by a factor of n. So we can easily find a bound for the spectral norm by n, because the entries of L are just 0 plus minus 1. And the spectral norm of L inverse, we bound similarly. We also use this norm equivalence. And then the max norm of L inverse, because the entries are just the number of paths, is exactly equal to the maximum number of paths between two nodes. So we find that this matrix L is exactly polyconditioned if and only if the number of paths between any two vertices is polynomially bounded. Okay, and for context, so this these path restrictions have been studied before. So the best known classical bound decided as T-connectivity, so not to count the paths, was given by Allende and Lange, and the algorithm was slightly generalized by Gavin-Souli, Tevari, and Vinochandran. And their algorithm runs in space log squared n over log log n. So recall Savage gives log squared n, so they slightly beat Savage in that case. And in fact, we were very amused when we saw that Eric Allende 2 years ago, he gave a farewell talk where he recapped some open problems he encountered throughout his career. And he offered a $1,000 reward exactly for improving this log squared n over log log n bound. Okay, let me also mention that I don't want to get into the proof, but it's actually a relatively easy corollary, that we can also verify if a graph satisfies this promise, whether the path count is bounded polynomially between any two vertices. So in fact, we get a language containment in quantum log space. And this is interesting because all previous problems which were considered were inherently promise problems and not language problems. So yeah, this is a small list of problems. Most of these are some linear algebraic problems, and then from this space-efficient QSVT paper, they presented some BQL complete problems based on state testing. Okay, let me mention one more generalization of our results so we can relax the condition of the number of paths being polynomially bounded between any two nodes. We can, it in fact suffices to only demand that the number of paths which are outgoing from S and the number of paths which are incoming to T are polynomially bounded. So how can we do this? We again consider this matrix A, identity minus adjacency matrix. And then we can write it in its singular value decomposition. And we pick some threshold kappa, which will be some 1 over poly. And then we look at the inverse of L, and we split it up into some ill-conditioned component and some well-conditioned component. And it is relatively straightforward to show that Tashma's algorithm for a poly-conditioned matrix inversion actually extends to the case that it can also get as input arbitrary matrices and then only invert the well-conditioned part. So one natural idea would be, can we just return some effective inversion where we only invert the well-conditioned part? And then maybe this gives a good estimate for the actual inverse entry ST, which would be the number of paths. And intuitively, this is not obvious at all, because the smallest singular values of L, of course, correspond to the largest singular values of L inverse. So we are really kind of leaving out the most important part. But it turns out to be okay. And why is that? So if we look at this vector here, ra S times L inverse, so this is a vector which corresponds to the S row of L inverse. So it contains as entries the number of paths from S to any other vertex. And of course, by our assumption, all of these entries are polynomial. So also the L1 norm will be polynomially bounded. And then we find that the overlap of S with Vj times sigma j inverse will also be polynomially bounded. Otherwise, there would be some index I, which would have high overlap with Uj, and then we would find that there would be a super polynomially many paths from S to this vertex I. And similarly, we also find that the overlap of Uj with T times sigma j inverse will always be polynomially bounded. And then if we combine the two, we multiply the overlap of S with Vj and Uj with T times sigma j inverse, we can get a bound of sigma j times poly n. So in particular, for very small singular values, we see that their contribution will be very small. So if we just choose the right kappa 1 over poly n, then we find that the small components don't contribute much. Okay, so let me now give some more context on how this result relates to some classical complexity classes. So I already mentioned an NL computation can be seen as a walk on the configuration graph. And then we can also make restrictions on the number of accepting paths. So maybe the most famous class on the slide is UL, where we require that we have at most one path from S to T from start to accept. And then there's also a more relaxed class, which is FUL, where we allow for polynomially many accepting paths. There's another class which has been studied, which is reach UL, where the condition is a bit stronger, that we want that the number of paths from S to any other vertex is bounded by 1. So in particular, this example chosen here for UL, for example, would not be a reach UL graph because there would be 2 paths from S to this bottom vertex here. And then there's also strongly unambiguous log space, where we want that the number of paths between any 2 configurations is bounded by 1. And again, this reach UL example here, for example, would not be strongly unambiguous because there would be 2 paths from this top right vertex to T. And then there's also the relaxed few versions of reach UL and strongly unambiguous log space. And yeah, in particular, this strongly few log space version is exactly what we had in our first main result. and then you can relate these classes as shown in this diagram. I don't want to comment on all of the inclusions, but they are really straightforward from the definition. For example, strongly unambiguous log space is contained in strongly few log space because yeah, here we have the condition less or equal 1 and less or equal poly here. Also, strongly few log space is contained in reach few log space because the reach condition is weaker than the strong condition. Okay, and then yeah, our first results could be seen as showing that strongly few log space is contained in quantum log space. And yeah, I already mentioned this classical result. Eric Allender and Klaus Lange, they showed that reach UL is contained in D space of log squared n over log log n. And then later, Garvin, Stoli, Devari, and Vinod-Chandran, they showed that reach UL is equal to reach few L. So yeah, there being only polynomially many paths starting from S doesn't make the problem any more difficult than if there are only one path from S to any other vertex. So then kind of this diagram contracts since reach few and reach U are equal. And we can put VQL on this branch and this D space log squared n over log log n bound on this branch. Yeah, so let me mention some open questions. One obvious open question would maybe be to go for this $1,000 reward and try to improve the classical upper bound, which in fact is offered for the most restricted case where there's at most one path between any two vertices. And then another problem, of course, would be, can we maybe further relax the path constraint in VQL? We already showed that we can have this reach condition, that there's few outcoming and incoming paths. Can we go further? And also, I think another interesting question would be to find a simultaneously time and space efficient quantum algorithm for STCon. So there's this one algorithm by Barnes and others, a classical algorithm which runs in polynomial time and slightly sublinear space, like n over 2 to the square root log n. And yeah, I think it's a very natural question if we can maybe quantumly improve and get a polynomial time square root n space quantum algorithm. And yeah, that was my talk. Thanks for listening.